This demonstration will focus on the manufacturing process simulation of an automotive part. This babilla will be manufactured using a resin transfer molding process. PAM RTM software is dedicated to simulations of RTM processes such as injection or infusion. It gives the opportunity to test different process injection strategies and to optimize the chosen one. This virtual testing can reduce drastically the number of real costly tryouts. PAM RTM integration in CATIA V5 environment make very easy the computation of the material properties with an automatic transfer from the CPD definition of the part. We can see here our B pillar in the composite design workbench. This is a typical automotive part, okay, and we will display also the different zones and the different zones for the layup. There are 4 main zones in the lower area, in the central area, in the upper area, and the top zone of the part. This is also the outlines of the flat pattern for my different plies. We can see there are 4 plies for the main part, 4 reinforcement in the middle area, and 4 reinforcement also in the upper zone. For RTM simulation, we will switch to the RTM workbench. In analysis and simulation, resin transfer molding. PAM RTM gives the user the opportunity to conduct different simulations, such as resin transfer molding, standard RTM process, vacuum assist resin infusion, heated RTM, preheating simulation with no injection, and curing analysis. In our case, we will focus on the RTM analysis. The next step is the generation of the mesh, and I will switch to the advanced meshing tool. I will choose to use advanced surface mesher, and I will select my geometry in my initial definition. This is the B-pillar surface. The meshing parameters, mesh size is 8 mm, and I will create a linear triangular mesh. I will use also some constraint to have some nodes defined on my injection lines. I will define the injection lines used here in the design, which are located in the top area, but also in the bottom area here. Okay, I can now generate my mesh. This is a very quick operation. It's already completed and it has created 23,365 elements. Okay, I can exit this workbench and enter again my resin transfer molding workbench. The next steps are the definition of my materials, the resin. There is 2 material definition parameters, which are the density and the viscosity that are needed for a standard RTM analysis. I will use those values. And for the reinforcement, I will get the information from the CPD definition, and using this link here, I will read the content of my initial design, okay, which is defined on those surfaces. The orientation method will be using the CPD rosette orientation, and the core sampling depth is the default 10 mm. Material file, I have to choose it in my list here, and I can press OK. Now I can generate the link with CPD and the mesh. Okay, and this will take a few minutes. I will now check if the link with CPD has been correctly done by displaying the number of ply, for instance. Let's try to display the number of plies on my part, and I can clearly see that in the top and the bottom zones there are 4 plies. In the central area we can see 8 plies, and the upper zone we have 12 plies as defined in the CPD file. I will deactivate the visibility of the number of plies. I can also show and display the permeability tensor, in particular the direction K1, which is displayed here with arrows. We will now have a look at the material database where information on the material are stored. We will open the CAT material file and displaying properties on carbon. Okay, we have some information on composites. This is material type unidirectional, and curd thickness. We have also some information about structural properties, and clicking on more gives access to an RTM tab where we get the information on the permeabilities. Okay. I will now deactivate the visibility of my permeability direction K1 and keep on moving with my definition of my data setup. I will create some groups for the inlets. For the inlets, I will be using the lines on the top and at the bottom of the part. So I will create groups using those two supports, those two lines, and we're giving a name inlet. I will do the same thing for the outlets. I will call it vents, and the support will be the boundaries on my bottom area, the two extremities, and the two extremities also on my top area. Okay, I can now reduce the design here and focus on the definition of my process. I will use for inlets a flow rate condition. The support will be the group called inlet. The flow rate, the default value is okay, maximum pressure is satisfying also, and the temperature is 300 Kelvin. For the outlet, I will use my support vents and a pressure of 0 Newton meter square. Okay, my data setup is now complete. I can launch a simulation. And I will compute the mesh and analysis. Okay, this is displayed here, the log file from the solver, which gives the output, a quite readable output. Now we've got 7% already filled, 8%, 9%, and the full simulation will last for approximately 8 minutes. The content of this log file is not limited to information written during simulation. It also gives some results, such as volume of resin used and volume of resin lost through vents during injection. My simulation is now complete, and I can now display the results, showing, for instance, the filling time, okay, here we have a filling time of 585 seconds, as my injection lines are located in the bottom zone and in the top zone. Okay, we can see also choose to display the flow front. I will hide the filling time and make a movie. And we can see in red how the resin flows inside the part. As my vents are located on the extremities of the bottom area and of the top area, my flow front ends here. But as I created the void initially with my outlet parameter, then I do not have any air at the beginning of the injection, so I won't have any air bubbles. If I had not defined the void, an initial void, I might have seen some air bubbles here, and in this case the flow front would not have closed in the middle area.